that has then been applied this G, which is the thresholding function, that will give out what the perceptron will say is the answer. You subtract that from T, you square it. That's what you really have. And you try to minimize this with respect to WJs, WIs, the weights. So now the WI is inside of G, which is inside of a square. Right? So if you want to do chain rule, now you have to do it 3 times. First you do the differential of the square, that will be 2 times whatever is in the square. Right? Then you do the differential of the G, which happens to be your sigmoid function, and I told you that you can actually do it from first principles, but it happens to be g of x, g dash of x is g of x times 1 minus g of x. So I'll assume that g dash can be done, and then I'll finally do the differential of this linear summation, but only with respect to the weight that I am differentiating it. And just as before, only term that will survive would be the one that Wj is multiplying, which would be the feature j or the input ij. Right? So after the 3 steps, essentially you will say the t minus o is coming because it is the inside of the square. Okay, and you have g dash because you have g has to be differentiated, and then when the inside of this is differentiated, you get ij. That's your update rule now. This looks almost like before. It's like alpha times the gradient, where except the gradient is not just the error, it's the error times, previously it was just the error times the feature value. Remember? And because g dash happened to be 1. It's an identity function. Now g dash is actually has a value. You throw that in, then you have essentially a dynamically changing alpha. So alpha times g dash is the new alpha, which actually changes based on where you are. This is called the perceptron, linear perceptron update rule. And this is called this is sigmoid perceptron update rule. But you notice that the update rule looks very similar. There's almost a structure to it. You have the error, you have the feature, if it's linear, as long as it's linear summation, which is what perceptrons do. Okay? And then there is this alpha, which is the learning rate, and then there's the g dash part. This is the original reason for craziness about neural networks back when I was born in 1960s. When a guy called Frank Rosenblatt figured out that these kinds of perceptron units can be used to learn lots and lots of functions. Not all functions, but he figured out a bunch of things can be done, and he was very happy. Until a couple of other people basically threw cold water at him and said, look, it would not be enough to learn all functions, it would be enough actually to learn only the classifying problems where you can draw a line at a hyperplane between the positives and the negatives. It should not be surprising to you, because what it is doing, what the perceptron is doing when it finds the final weights, is it essentially saying Wi times ii sigma greater than some threshold. If it is greater than some threshold, it's yes, otherwise no. That defines a hyperplane in the j dimension, in the space that is of the same dimensions as the input. Okay, so this is linear perceptron. We sort of started from reinforcement learning, online learning, we came to linear perceptron. I want to end by pointing out this very dense slide that you get to read, but essentially most of the things are pretty obvious here, that if you're trying to learn function f, and you're trying to predict f dash, f hat, okay, then you want to compute the error, and then minimize the error. you get to define the error in any which way. You could have defined it an absolute value, or the squared, or the power 4, etc. And depending on the way you define the error, the differential, which is the weight update rule, will change. The aggregate error function that you define is called the loss function, which is the name of today's code. The parameters Wi are changed in the direction opposite to the gradient, where the gradient is computed from the first principles, for now at least, of calculus. And the gradient itself, as we saw, depends on the form of the loss function. Is it a squared loss function? And the form of the threshold function. The other thing was, I also said for the RL that it also is a linear function. I don't have to say that here because perceptrons only do linear summation of the inputs. Each perceptron unit is a linear summation of the inputs, linear weighted sum of the inputs. The beauty of perceptrons comes if you stack them such that this guy's output goes to somebody else's input. That's where you get multi-layer neural networks or deep learning. So coming back to this, the simplest loss function that we looked at is f hat minus f squared. That's the square loss function. But there are many other loss functions. In particular, in the case of classification, you tend to look at, as I said, logistic regression, for example, can be seen as essentially providing a probability that this is class A versus class B. Which means you can think of the perceptron output as a probability distribution. The true distribution is known, because you know whether it is actually 1 or 0. So you then have to compare two distributions. So in fact, in general, whenever you are doing errors, you are taking the distance between two vectors. This is the L2 norm distance between vectors. The squared error is L2 norm distance. Absolute error would have been called L1 norm distance between the vectors. For distributions, for probability distributions, which are also vectors, in addition to these LK norms, you can also start thinking about entropy functions. And in particular, there is this crazy looking function called cross entropy, which is the true value, the true distribution times log of the value that you actually computed. And similarly, true value for the second distribution, second value in terms of the true distribution in the log of t. We'll go through this again, but I just want you to understand that this is called the cross entropy loss. This would have taken place instead of the squared error. If you did this computation, instead of this square, you put the average summed cross entropy loss, and then you went through the steps, and you got a gradient update rule which doesn't look that much different, then that would be called real logistic regression. Now, of course, notice that in this other guy, you have logs. So you have to now start differentiating logs. Do you know what is a d by dx of log x? You never should forget this. It's going to be useful lots and lots of times. So if you do that, that becomes logistic regression. Okay? We will stop here. 1 full week after, we will again get back.